This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello and welcome back to Construction History. Today we'll continue to talk about glass, and we will see how glass, particularly in the 1800s, has been used by looking at a very important building most of all, but also contextualizing how this building has made a big difference also in the construction, in the history of construction, as well as, of course, in that of architecture and even that of engineering. Now the building I'm referring to is the Crystal Palace. So in this lecture we'll be looking in prevalence at the United Kingdom, Great Britain during the mid 1800s, and in particular we go through the pathway that took to the conception of a very significant piece of work, which is the Crystal Palace. And we will see how that project eventuated, with a particular regard on two aspects. First of all, the unique method of procurement that took to the completion of the Crystal Palace, and also the very innovative methods of construction that were bound to have a lot of influence, both from a technical perspective, but also from an architectural perspective, broadly speaking, and even, I would say, from a urban design point of view. So we will conclude by having a brief discussion on the legacy also of the Crystal Palace. But before we talk about the Crystal Palace, we have to contextualize what's happening in the 1800s, in particular when it comes about the use of glass. We already understood the methods of production of glass of the 1800s. We looked at some methods of blown glass in particular, and we saw how the blown glass methods of construction of older origin were somehow approaching methods of productions that became more and more sophisticated, and manufacturing that started to take the first signs of a mature industrial method of production of glass. In combination with the growth of these abilities to manufacture glass with greater capacity, with greater skills, with better quality assurance, in the 1800s in the United Kingdom in particular, as a result of the tremendous growth induced by the Industrial Revolution, as well as by the political and global power of Great Britain as an empire with colonies all around the world, this political and national somehow inputs have created conditions for the proliferation of new building types. And one of these building types was the conservatory, or the greenhouse. In other words, a place that could recreate in sun-starving skies of Great Britain some of the conditions that the British could find in their colonies scattered all around the world. So obviously this trend to recreate this artificial environment to host nature became more and more important, and more encouraged, and more also by the development of sciences like botanics and the encyclopedic thirst for knowledge that was characteristic of those years. So in this context, we see that there is a number of buildings that have been produced and designed that somehow had to recreate the internal conditions that were favorable for hosting plants that would not have been able to grow otherwise in the climate of the United Kingdom. Now, one of these was the Great Stove, a building designed by a gardener, Joseph Paxton, who was at the service of the Duke of Devonshire, who also developed not only and took care of the gardening aspects of these buildings, but also and started to develop systems that were construction systems suitable to maximize the input and the benefit of exposure to the sun. Now, the Great Stove unfortunately does not exist anymore, but was a magnificent example of this greenhouse architecture, entirely glazed, typically with cylinder glass, and also using these curved profiles that were studied on purpose to maximize the amount of penetration of light. So this would happen normally with these rib profiles that are like a folded plate, in this case curved, and you can see here between the ridge and the gutter lines of this envelope you have a series of glass panels. Now, Joseph Paxton developed, as we said, this system specifically for application in greenhouses. Now, the benefit of this folded profile is that by having an angle that is designed according to the sun orientation, there is an opportunity for the sun to enter the greenhouse by having an angle of incidence against the glass that is perpendicular at least twice in a day. Now, the angle of incidence of sun rays is very important to maximize the amount of energy that penetrates through. And the merit of Paxton was that he conceived and understood and took opportunities of the developments in iron and glass, so that he created envelopes for these greenhouses that were maximizing the amount of gain of light from the sun. Whereas traditionally the first greenhouses were characterized by fairly heavy rafters or framing members for glass that were more traditional, but that also created rather dark environments. Now you can see one of these first examples of Paxton employed in this building here, greenhouse Chatsworth being the residence of the Duke of Devonshire, for which Paxton worked at least in the first stages of his career. And you can see how he has developed this corrugated profile here, where you have sheets of glass that are following this pattern known also as the ridge and furrow system. And this method somehow evolved further to the point that Paxton was able to recreate conditions even of tropical environments. The most known of which is this particular greenhouse, known as the Victoria Regia Lily House, again in Chatsworth, where Paxton created an envelope, again using the ridge and furrow roof of glass and iron, and an envelope all around the perimeter that is like a curtain of glass supported infilled by cast iron and archways. Now, this episode is somehow very well known, and it shows the ability of Paxton to host species that would have been very difficult, if not, of course, impossible to have in a normal environment in England. Of particular interest was this lily that was able to float on the water as a result of its profile and as a result of its nervature. Now, this was an example of the wonders and the ability of this English gardener to recreate artificially conditions that were not possible before. But in this particular case of the Victoria Regia, Paxton also grasped some ideas that will become very important for the Crystal Palace. These lilies floating in the water are notorious for their ability to be relatively strong, to the point that Paxton was able to demonstrate the strength of this natural wonder by having his daughter any, in one instance, to even step on the lily to demonstrate the ability of these lilies to support a weight. Now, the ability of the lilies to support the weight is in virtue of what happens on their underside with this. This is very strong nervature of that nature has recreated to support the leaf and let it float. The nervature is stronger in the middle, and it progressively branches out, becoming thinner and thinner towards the edge, and the edge is then folded up to create this self-supporting and standalone structure. Now, looking at these marvels of nature, arguably, or at least anecdotally, it appears that Paxton to some ideas of skeleton construction. So the idea that you can have members that can be simply supported with a trabeated approach that is not necessarily mimicking nature in virtue of the way it looks, but in virtue of understanding how it works as a hierarchical system of structural members from primary to secondary, and also by using very simple means that are repetitive. Now, this is the background from which the designer of the Crystal Palace comes from, a gardener turned into an architect and an entrepreneur, and eventually also elevating himself to the aristocracy, even becoming a parliament member as a result of his long life achievements. Now, the history of the Great Exhibition, however, started without Paxton. So the Great Exhibition was conceived in England as an opportunity to showcase the wealth of the nation and its remarkable international connections all around the globe. It was the first attempt to create what today we would define as the Expo, or a world fair that would have representatives from all the nations invited to showcase their cultures and their goods for commerce. Now, the World Fair, this idea of the World Fair was somehow initiated by a Parliament member, Cole, and as a result of a decision of Parliament to initiate this world exhibition, a building committee was set up, and a competition of ideas was released and announced. Although the competition had a fairly narrow period of time for submissions, the submissions received were numerous, at least 250 to 300. It's still not clear how many they were. And one of the ones, there was actually several interesting schemes that were shortlisted, and the winning scheme was awarded to a French architect, Hector Horot, who you can see his scheme here at the top, who devised this portal frame, triangular, a very large hall in section that obviously had iron structures and glass as the main materials of construction. The scheme, however, turned out to be not competitive enough, to the point that the committee felt the necessity to award the scheme to Horot. Horot was awarded a prize for winning the competition, but the committee preferred to, rather than giving the job to this French architect, preferred to steal somehow all the ideas gathered in the competition and set out to propose an independent scheme, which is the one you see below here. Now, the so-called official design of the competition was a bit of a hodgepodge of different ideas sort of mixed together, one of which also had an enormous dome of iron that would have been possibly the largest dome at that time in the world. The scheme also had a strong reliance still on masonry construction, and it was somehow a product of mainstream architecture of the time. Now, the building, however, turned out, even the official scheme turned out to be way over budget and with some significant challenges that made the construction of this hall for the exhibition impractical. Now, one of the key aspects of the competition was to have a building that was able to be dismantled. The exhibition should have taken place in Hyde Park, and at the end of the exhibition the idea was to remove whatever was installed there to give the park back to the city. Now, this created some significant problems to the point that no contractor really was able to price a building like the official scheme on tender. Now, Joseph Paxton at that time, he did not submit any scheme. He was not an architect. After all, he was a gardener specialized in greenhouses. But he was a very well-connected man in England who heard about this potential debacle of the competition by not being able to award and have a building that was completed on budget and on time, whilst time towards the opening time for the exhibition was ticking. All these factors was putting the project and the whole exhibition at risk to the point that it might have to be cancelled. So Paxton somehow, due to his acquaintances with the upper echelons of British society, was able to hear about this problem, and he somehow almost half-heartedly said, well, I think I might have an idea in mind on how to resolve the problem. So this is not necessarily anecdotal, it's actually a fact that he somehow sidelined and the whole process, and by using his connection he was able to win himself the interest of the commission to present a scheme. Now, the scheme that he presented also was apparently developed on a piece of scrap paper, basically during a meeting in the railway board and so Paxton apparently sketched this whilst hearing a disciplinary proceeding of the committee. And in this scheme you can see there are some elements of, this is a section and a corresponding elevation of a building that is indicating the folded furrow, region furrow profile of the roof, a series of posts and semicircular arches that is reminiscent of the house for the Victoria Regia we saw before, and a hall that is divided in three areas: a main nave and two side aisles. Again, yes, a scheme probably reminiscent of the scheme of Horreux, but with a very different technical approach. There is a repetition of elements, there is an orthogonal approach, and there is this very deliberate attempt to incorporate all the knowledge of greenhouse design that Great Britain had developed up to that point. So, in parallel to this, now the napkin or blotted paper sketch obviously was not what Paxton submitted, but whilst producing these ideas and starting to work, because Paxton had at his service a whole entourage of not only of gardeners but also of technical support, including engineers that were able to work in cast iron and produce also drawings. So Paxton somehow started to document the building even before he had been given the job, and in parallel with that he also reached out to the media using his connections, and he released this scheme in the news, in the Illustrated London News. So when this scheme was published, the public reception was enthusiastic. It was immediately dubbed as the Crystal Palace even before it was built, and this scheme, so bold and repetitive, almost relentlessly, just creating sheer space and sheer mass and volume by using glass on an unprecedented scale. Well, this scheme was an incredible contrast with the somehow over budget and hard to achieve scheme that was a mix of different themes that the commission had put forward. So in this context, Paxton eventually was awarded a project on his ability to create a concept for a construction that was fast-tracked And that was somehow not developed enough. We would probably define this as a very similar process to what today we call a design and build project. So we have a scheme that is a vision. It has a very simple articulation of the spaces inside that can be easily conveyed. There is a lack of construction detailings available, but there is a systematic approach to the design that can be developed even without understanding the details as yet. And so in order to proceed and win the job was eventually awarded to a contractor, Fox and Henderson, but also on the basis that Paxton was engaged with a glass manufacturer, Robert Lucas Chance, who had his factory of the Chance brothers in Birmingham, or nearby Birmingham, and Paxton was able to strike a deal with Chance to produce glass of an unprecedented size outside of the standard range of what was available that day, and very much take the Chance brothers to focus all their efforts on the production of glass solely for the Crystal Palace over a certain period of time. Again, this was an approach to design and construction that was unprecedented, and that showed the ability of a designer who was also an entrepreneur, who was able to develop the project from the beginning by creating a one-off exercise that is, yes, standardized, but it's also customized for the specifics of the job, and this is possible due to the large scale of the project. Now, the Chance brothers used to, as we know, produce glass known as broad or sheet glass using the cylinder glass process, where cylinders were blown but then swung to a certain length inside pits, so they were elongated into a cylinder that eventually was cut and then put inside an oven where, as a result of the heat, the cylinder would flatten out and become a sheet of glass. Now, the illustration before was produced to give an idea to the public of the glass produced for the Crystal Palace, but the previous image doesn't show exactly what really allowed the Chance brother to achieve glass that was cylinder glass that was bigger than what was available at the time. There are two aspects here. First of all was the availability or skills of French glassmakers that Chance was able to bring over from France when he set up his factory. And for the Crystal Palace, he had to go and source even more French glassmakers to achieve this. Now, cylinder glazing also was achieved using this apparatus here that was able to help the glassmaker to swing them and to a length that was longer than what was normally available at the time. The skill was remarkable because here we're talking about a manufacturing process that has to be repetitive and fairly accurate at the same time, because all the panels for the glass of the Crystal Palace had to be somehow within a certain dimensional range that allowed them to be fixed and reproduced many times with some certain accuracy. Now, this was the final scheme of the Crystal Palace, where you can see now the concept that started on a blotted piece of paper, is starting to take shape. But you recognize that that sketch is still intact, for the exception of this other member or part of the fabric, which is known as the transepts that cut across orthogonally through the initial idea of the Crystal Palace proposed by Paxton. Now, the Crystal Palace was the biggest thing that was ever built, possibly in the world, and it was an enormous footprint. We're talking about a building that was 1,848 feet from center to center of the column, but exactly was actually 1,851 meters long to indicate also the year of the opening of the exhibition. and 408 feet wide. So this translates to 560 by 125 approximately footprint. The building, as we said, was very simple. It has 3 main spaces, a nave and 2 aisles, like a church, like a cathedral, and a transept here that is covered by a barrow vault just in the middle. And you can see here the pictures of one of the gates and the entrance here of the transept. You can recognize now how the sketch has evolved into a series of archways supporting glass panels here of cylinder glass produced by the Chance brothers, and this marvelous transept here that is covering the central part of the space. Now the transept was off-axis, and it was introduced also to preserve some existing trees that were left on the site in Hyde Park. Many other trees were had to be removed, and to the protest of some local residents, actually, one of which remained in place even during construction for a period of time. So some of these trees, however, were saved, and the transept became somehow the central focus also of the building. Now you can start to appreciate here also the construction of the system here, where you see of this building, you see a series of trusses, and you see a series of cast iron posts that support this very simple filigrane of iron and glass. Now the building was successfully opened in the 1st of May Day, 1st of May of 1851, by Queen Victoria, who enthusiastically welcomed the completion of this marvel of construction. The building of Crystal Palace became much, and still is, an icon for architecture, perhaps as the first real modern building, or the building that somehow anticipated the things of modernism. But certainly for the contemporaries, it was a feat of construction, first of all. If anything, was very remote to what at the time was an understanding of architecture. And nonetheless, this struck really a chord of the culture and the changing culture in the construction industry at the time. These are the years of iron and concrete becoming new materials. These are the years of a large infrastructure. These are the same years in which, in Britain, impressive bridge constructions are built, as we saw before. So this moment really signals a point of change. But really, as we said, what really remains of this building is the incredible ability to put together a building of this size in nothing less than 17 weeks of work. So how was it built? Well, it was all about really modularity and prefabrication. So the building was based on a repetitive module of more or less 24 feet, then broken down further into elements of 8 feet. And then it was using simply 2 materials, iron and glass, where iron was a combination of cast iron and wrought iron. And the glass is the same glass that we already discussed, the cylinder glass produced by the Chance brother. So blown glass, but blown to a dimensional standard that is pre-industrial, if not already industrialized. So this building, you can see here the basic elements of 3 levels that are sort of stacking and repetitively on one on top of the other. Yes, the exception of the transept that becomes the focus of the composition. But a building system that is ultimately relentlessly repetitive. And a building system that is a post and lintel system, really, of columns and horizontal beams, but that in order to become stable against the wind was also using some bracings of wrought iron rods. Now the building was installed directly on the park by using some footings of the columns that were dug, and then there was a base element that allowed the cast iron columns to be bolted on top of it. As you can see here, this is a picture of how the construction starts directly on the park. There is no slab, there is simply the posts are driven directly into the ground, sitting on a very simple footing that is not visible, and then the building somehow springs up from the grass in this case, or from the earth. And this was because the building had to be assembled quickly, but also dismantled once the exhibition was finished. You can see here one of the working drawings that were prepared, in this case by the contractor, Fox and Henderson. Again, this is important to stress, showing the sort of design and build approach for a building that was never done before. The concept of Paxton had to be design developed, and in this case, it was the builder who developed this particular schedule of columns that remain the same in diameter from floor to floor, but that they change the thickness inside. So obviously to respond to the additional loads as you go from the top floor to the lowest floors. And you can see here a picture where a worker is working around these columns. You can see how they're coming off the ground here. There will be a little footing pad below onto which they are connected. You can see here a fixing a gusset plate that somehow reinforces the connection. And the columns were then in cast iron were bolted through this base that was cast specifically for the project. And the cast iron being hollow were also the place where stormwater drainage would come through. It would just come down inside the column, and then it would be reticulated at the base using this pipe. So you can see the worker here is basically sealing this the connection of the pipe using molten lead. Then the rest of the construction was a series of girders or trussed girders, of which there was several sizes that were installed again in a dry fashion. They were all prefabricated, and they were used simply by having an approach that was using very simple craning systems and some suspended pulleys that were able to allow workers to install these girders. Now you can see here how they're operating, and you can see this worker is he's got something in his hand. We'll come back on that to describe also how the connection worked. And this is how the connection worked, where you have a truss girder here on the side. It's been, in this drawing, it's been broken up. This is the cast iron column, of which you see here a plan, and you can see it's hollow inside, so it was also collecting rainwater. And the cast iron column terminates with this joint that has some connecting pieces, again of cast iron. There are some bolts that connect them onto the lower part of the column. And so this element you can see here is basically a shoe that is allowing it's basically allowing the girder, which is coming from this side, to connect, and with the driving on some wedges or pins or wrought iron or wood, the girders becomes fixed at this point at the intersection with the column. So this was a connection that was dry. There was no riveting involved, no welding also, because this is cast iron. You cannot weld cast iron. But it is a rigid connection that is allowing the structures to become self-supported as you proceed. So and also in a very efficient way that also allows this wedging, these iron keys to be removed for dismantling the structure later on. And this is the view of one of the naves here, where you can see how all the system is happening. You have columns here and 3 stories here. There's a gallery on the upper floor, and then there's further up further more space that takes to the roof. And you can see how here you have the columns and the girders coming together. Now the other very important part of the Crystal Palace was, of course, its roof, which was repeating some of the things that Paxton devised for his greenhouses at Chatsworth. And this was the idea of having a roof that was again a folded plate that was alternating ridges and valleys, or the ridge and furrow system that we said before. Now this system was based on a very simple method of construction. We had a 24 by 24 feet grid in both directions, so it's a square bay where you have 24 feet both ways, and we have, of course, the cast iron columns that we described before. Then we have the girders that span from cast iron column to cast iron column, and then we have something that was an invention of Patton himself, which was a patented timber gutter that spans between two girders. And this timber gutter is then supporting the glass panels and a ridge element in the middle that again, allows to have this sort of undulated zigzag pattern on top of the roof. And then you can recognize here you have glass panels here, which were exactly 49 inches by 10 inches wide. But they were produced from a cylinder glass that was 3 times as big. So the Chance brothers produced sheets that were 49 by 30 inches, and then these cylinders were cut in 3 to produce panels that were smaller and easier to handle inside. So here is some more information about the trusses. Now the trusses were composite. They were a combination of cast iron and wrought iron, because cast iron and wrought iron have very different performance and properties, particularly when it comes about tensional stress. Cast iron is strong in compression, but its tensional stress is an eighth of its compressive strength. So Paxton, but not so much Paxton, more Fox and Anderson in this case, the builder, design builder in this case, devised a series of profiles then, and it's a combination of profiles in cast iron and wrought iron depending on the stress behavior that was required. Now the trusses were modular. There was 3 sizes. They were either 24 feet or 48 feet or 72 feet. So in other words, they had a relationship of 1, 2 and 3 with a basic span that was added up as in a modular fashion. Also the trusses had this very interesting profile where they were taper at their end, so they had this swelled middle section that was built on purpose bigger to pick up some of the additional stresses that inevitably they would have at mid-span. So you can see here some of the drawings produced by Fox and Anderson that are somehow giving a schedule of the different combinations of elements and how this creates cords and webs that then become trusses of iron. And in the other direction of this ridge and furrow roof, there was the gutters that we already described, and this was the result of the patented system that Paxton developed. They are timber gutters that are scalloped in the middle, and they fall, of course, like a gutter, but they have something else that is quite interesting. At the underside, they have a series of support points for a wrought iron rod that is creating a tension, and it's inducing a camber on the gutter. So the wood is bent or pre-bent, giving a cambering, so that there's an ability to withstand the span or achieve a larger span with minimal effort. So this is a forerunner of pre-stressing and using timber and iron. So a composite approach again, like in the truss girders, but this time used in the gutter. And then you can see how between the gutters you have glass panels falling at a 1 to 5 pitch, and that are connected by a ridge here. You will notice that there is no support under the glass because this is working like a corrugated plate. So again, this is the incredible skill of the inability of Paxton and his team to conceive buildings that are working with minimal amount of structural elements, a bit like nature, again, a bit like the lily flowers that he observed in a tank in one of these greenhouses. Now, what was also remarkable about this roof, it was the way it was built. The initial approach to the construction, which involved some 19,000 pieces of glass to be installed and glazed manually using putty at that time. Initially, the building was glazed using a series of planks spanning in between the girders, with workers just obviously been working on these temporary platforms and using ladders, of course, with great risk to their safety. But not only this was not so much safe, but also it turned out to be quite slow given the amount of the area of glazing involved. And so Fox and Anderson in this case devised a very unique approach to glazing, where they created a glazing wagon, which was a traveling stage able to span from two gutters of the roof with some wheels. They actually used the profile, the scallop profile of the gutters as a track. Then on these carts, there was 4 people. They were able to sit and complete the glazing. Interesting enough, being in England, and the building was completed towards the late autumn and early winter of the 1850 and 1851. These carts were also furnished with a rib here that was able to host a cover to protect the workers from the rain. Now, the other feature of the building, of course, was the transept, which was a very interesting exercise in itself. It had, unlike the rest of the building, it had some ribs of laminated timber, one of the first examples of that, and then it was subsequently glazed with a system the same system that more or less we described before, but in this case following the curvature of the transept. Now, the transept was a perfect semicircle, a bar vault, and it was lifted up using some cranes that you can recognize here, using this procedure here, going from obviously using 2 bays at the time. So again, having an approach to prefabrication to speed up the erection. Now, the transept had an interesting feature too. At its base, it had a series of louvers that were operable using a mechanism of cogwheels and wires. So you can see here the glazing of the transept. You can see these sheets of glass running in this direction that have been cut off at their ends to have this pattern. Now, these ridges are protruding towards you as you look this. So this is a ridge of the glazing of the transept, and this is a gutter that eventually discharges on the roof below. And you can see here the sequence of glazing of the transept, where you go from the specification and understanding the design into the installation of glass, the installation of another glazing strip on top of it, and eventually some adjustment and the completion of the work. And this is a close-up of the working drawings, again produced for the louvers, that allowed an operation and some ventilation to be provided to this space, so that there would be some relief. Now, the Crystal Palace was dismantled as established in 1852. But the story of the building, the remarkable success of the building, made it such that there was a legacy of this building. Now, the building, in fact, was disassembled, but it became such an iconic a piece of architecture and almost a monument already to the city at the time, that it was felt the need to reproduce it somewhere else. So this was also an interesting twist, because the building became competitive enough to be built, because Fox and Anderson, the contractor, said, yes, I'll build it for the price that the committee has said, provided that once the building is finished, I can collect everything we've done and we can reuse it somewhere else. So the Crystal Palace was rebuilt in part in Sydenham, still in London, between 1852 and it was also altered, but still reused many of the initial elements. You can see here how some of the parts of the older Crystal Palace are being delivered. You can recognize here the columns with their connecting pieces, and you can recognize some of the girders here being stacked. And this is the Sydenham Crystal Palace being rebuilt. Again, you can recognize the same systems now taking place, but this time there's a more permanent sort of work underground to support the cast iron columns. Another thing that was amended into this rebuilt Crystal Palace was the transept, that was not laminated timber anymore, but it was conceived to become a more permanent structure of iron. Again, the same feature of the barrel vault, sort of semicircular arch, but this time built in cast iron and wrought iron. And these are some pictures of the construction of the transept that also caused some inconvenient moments during construction. There was actually some collapsing of the temporary structure that caused some casualties too. And this is again a picture that illustrates the brilliant solution found for the glazing of the transept, where you have the ridge and furrow method of roofing, and this time following the curvature that is along the ribs of the barrow vault of the transept. Now the building was a success once rebuilt, up to a point anyway. It became something that served the citizens of London for at least 3 generations. But in 1936, as a result of an accidental fire in a cloakroom, the whole building eventually burnt down to a great loss and great sadness of those who had to see this. And so the building was never recovered, of course, from this. There was nothing really left except from the water towers that stood outside of the footprint of the reconstructed Crystal Palace. But the building continued to live. The Crystal Palace became an iconic building, but also became an iconic event. It arguably initiated a whole series of new opportunities for showcasing, for international exhibitions, and most of all, it also demonstrated some of the remarkable abilities of new construction system to create spaces that could not have been conceived before. Now, one of the ideas that stem from the Crystal Palace, not necessarily the construction of skyscrapers, but it's interesting that one of the first ideas for its reconstruction was actually to re-employ all these parts of the disassemble modular structure of the building and reassemble them vertically, like in the form of a crystal tower. So such was the idea presented in a magazine in England in 1852, when the Crystal Palace had to be dismantled. But there was another Crystal Palace that really took place 2 years later, and there was the Crystal Palace of New York that had obvious continuity with the ideas of the English one, and that became, of course, the hall for the hosting of another international exhibition. Other things that stem from the Crystal Palace was some visionary proposals, including this, which is the Crystal Way, or a urban design idea to have a series of galleries interconnected with the railways, through which shopping could occur undercover. And you can recognize how this obviously led to the iron and glass arcades that we still find in many parts of the world. So this being, for example, one of the most renowned, which is the Galleria of Vittorio Emanuele Secondo in Milan, for example, one of the most elegant but most successful spaces also from a urban point of view, that allow to have this combination of iron and glass to provide an undercover space that can be used and enjoyed, and also encourage more shopping and more consumerism. Now, I will finish with these views of Galleria of Milano, simply to say that this obviously it's a building, the Crystal Palace, that had enormous repercussions internationally, certainly not only in Europe but also overseas. We could easily draw parallels, and in fact there are some parallels perhaps even with Australia that could be discussed further. So we'll conclude here now, and this will also conclude our discussion on glass in this particular module, although we'll come back on this later on. So as always, you'll find there are some readings on the Crystal Palace, but also on the methods of glass production that are relevant for this period in history.